thank you for the invitation to talk on this conference. I'm really sorry that I couldn't come in person. Hope to come some other point. I don't see people. I'm going to talk about our joint work with Ron McGonin, who I think is also here and who will comment if I make mistakes. It is on archive, and it is. I will tell you a story about representation theory, and at the end of the day, it is a rather concrete story. So we have concrete formulas to obtain concrete representation of a certain algebra. And this algebra is a toroidal algebra, or maybe better to say quantum toroidal algebra, and this is the simplest quantum algebra, quantum toroidal GL1. I will denote it by UQ-GL1 and put here two dots. I'm not sure they are very visible, but I think almost always when I have GL1, they are GL1 with dots. This algebra depends on quantum parameters Q1, Q2, Q3, which are subject of relation Q1, Q2, Q3 equal to 1. So actually it depends on two quantum parameters like Q and T in McDonald's story. And there are many motivations to study this algebra. I will spend maybe half of the talk talking about this motivation, because our problem comes from all these motivations, and I'll restrict myself to three motivations. First of all, this algebra is very related to spherical Hecke algebra. In some sense, there's a limit of the spherical Hecke algebra for GLN, where n goes to infinity. There is another point of view that this algebra is a limit of the large algebras, namely Q-deformed W algebras related to GLN. Here is another letter n, and this n also goes to infinity. It looks to be there is some contradiction between these two constructions, but actually it means there are two different. The difference between limits lies in some completion, and I ignore these problems for the talk. And maybe the most important motivation for at least for the problem was the geometric origin of this algebra. This algebra acts on the direct sum of the equivalent key theory of the Hilbert scheme of points on C2. And so our problem comes from this geometry. Actually, as I point that there are many other motivations. For example, currently the combinatorial applications of this algebra are very active in Hyman's works and Mielit's work and others, but three is maybe sufficient for my talk. And in the description of the conference, the main words were Poisson algebras, Vertex Poisson geometry, Vertex algebras, and geometric representation theory. And I should apologize, probably will be no Poisson geometry in my talk, at least directly. But geometric representation theory appears maybe in this point. And I will not have vertex algebras, but I will have Q-deformed versions. So in this sense, it is related to vertex algebras. But I will start from the motivation that comes to spherical Hecke algebra, because it lies somehow in the center of what I'm going to do. So I will try to do a bit concrete. Let me recall what is double affine Hecke algebra. I restrict myself to double affine Hecke algebra related to GLN. So it is algebra which has generators x1, xn, t1, tn minus 1, and y1, yn. T1, tn minus 1 generate ordinary, not affine, Hecke algebra. So each ti is subject of quadratic relation. I denote by v the corresponding quantum parameter, and also braid relations, which I mean here explicitly. And t's and x's, and both t's and y's, generate affine Hecke algebras, and the total is double affine Hecke algebra. So the relations between t and x is written here, between t and y is written here, and there are also some relations between x and y's. I wrote a sufficient number of them, but maybe I will not use the explicit form. what is so important thing to remember that this algebra has some sort of triangular decomposition. So a subalgebra generated by x's, then there's subalgebra generated by t's, and subalgebra generated by y's. But contrary to the usual story about simple algebras, now these parts are commutative and this part is not commutative. Another thing to remember that we also had parameter v in the quadratic relation, and in the relation between x and y's, we have one more deformation parameter which I denote by q. So this algebra already depends on two parameters q and v. It is maybe not clear from this definition. It's not clear from this definition, but it is more clear from the geometric descriptions of this algebra. But there is an action of SL2Z of group SL2Z on this algebra. Here you tilde, which means that it is a central extension of SL2Z by abelian group Z, some sort of the cover, but usually I mainly ignore this difficulty. There are two natural gradients on this algebra. One of them is a gradient with respect to x's, another with respect to y's, and SL2Z acts on this lattice gradient. Okay, so this algebra, and one of the first motivation of this algebra that is related to Macdonald's theory. The algebra has a standard representation. Maybe I should call it a Cherednik representation on the space of polynomials. I choose to write this space of polynomials on y's, and in this space y's are x by multiplication y's, and x's x by certain difference operators, which include permutations, which are called, could be called Dunkel operators, Dunkel-Cherednik operators, and the eigenfunctions of these x's are non-symmetric Macdonald polynomials E lambda. Okay, this is a story to non-symmetric Macdonald polynomials, but as I said, in order to talk about toroidal algebra, I need a certain subalgebra in the double fine Hicke algebra, namely spherical subalgebra. So I introduce symmetrizer S plus. It is a sum over all permutation. Here should be, I think, in capital, over all permutations corresponding elements in the finite Hicke algebra, and here is some factorial. Also should be on n capital. Sorry. And this symmetrizer I called V symmetrizer because the deformation parameter in my Hicke algebra is V. And spherical Hicke algebra is obtained by action of this symmetrizer post size. So this is important due to this normalization. This is a subalgebra with identity equal to S plus. This algebra has a, I mean, this is a definition of algebra, but now the question is to find description of generators and relations, and at least for generators, there's possible solution due to Schiffmann-Vassereau. They define generators which are denoted by PAB, and where A, B are integers. So we have quite a lot of generators. So 2 without 0, 0. And these generators are enjoy the following properties. So first of all, and maybe the most important, they are equivalent with respect to SL2Z action. So action of SL2Z on the spherical subalgebra just permutes these generators, acting on this index A, B. And this indices agrees with grading. So PB has A axis and B y's. And then it's sufficient to define just P0K, and they're just S plus, sum of y's in power K S plus. Okay, so this is a set of generators. It's not very difficult to prove that Z indeed generators. What is really non-trivial statement is to look at the relations, and it can be shown that this relation stabilize. So there is a certain algebra, which in fact is quantum toroidal algebra, and suggests there exists a surjective homomorphism from this algebra to the spherical algebra. S plus. And here also is plus. Okay, I forgot minus pluses. And this, so there are certain relations which are somehow, which disappears in the limit when n goes to infinity, and certain relations which depends on n becomes analytical and so on. And so, and there is an algebra which is a limit of this, all this stuff. And this is a toroidal algebra, which is the main object of my talk. I'm not going to write down it by its relation. So as I said, its generators are PEB. This quite huge list of generators. These are PBW generators. So any element can be written as a certain product. And therefore, the products form basis in this algebra. If it was the algebra, one could think that we defined already generators which correspond to any root, not just simple. And there are some relations which, as I said, I meet. Instead, I would like to say something about its representations. And first of all, how we can obtain representations from this point of view of starting with spherical Hecke algebra. So spherical Hecke algebra acts, original Hecke algebra acts on the space of Laurent polynomials. So spherical Hecke algebra acts on the space of symmetric polynomials. So here I formally apply V symmetrizer, but it is not difficult to prove that image of this V symmetrizer is the same as the image of the standard symmetrizer. So it is just the space of symmetric polynomials. So since this algebra acts on the space of symmetric polynomials, then since there is this surjective homomorphism, the quantum toroidal algebra also acts on the space of symmetric polynomials on variables. And here one takes the limit, again takes the limit when n goes to infinity. And in this manner, define action of the quantum toroidal algebra on the space of symmetric functions. Eigenvalues of the, we have generators PB. Here I put generators PK0 because they don't have 0 y, so they are just more or less symmetric function axis. And as I said, axes act by some different separator, like Dunkel operators. So these symmetric functions preserve the gradient and can be diagonalized all, and they're just Macdonald operators, and the eigenfunctions are now symmetric Macdonald polynomials. So okay, but to write Macdonald symmetric functions, but let me keep it. The eigenvalues here are Macdonald polynomials, and lambda are Macdonald symmetric functions. I spent some time explaining this construction because what we will do at the end is some relative of this construction. Not, I wanted to say generalization, but probably not, but anyway, relative. Are there any questions? Okay. Now I want to explain a bit how it is related to W algebras. Maybe I will not use it precisely in the talk, but maybe somebody will be interested in that. So we obtained representation of the space of symmetric function lambda. This space of symmetric function has a natural structure, standard structure of the representation of the Heisenberg algebra. So we can introduce operators a minus k, which acts by multiplication on pk, and a k, which acts by derivative with respect to pk, and this operator satisfy Heisenberg algebra relations. And in terms of all this Heisenberg algebra, we can write down action of the toroidal algebra. It is convenient to write not all generators, but subset which morally correspond to simple roots. So this P0b is like Cartan part. This P1 k, I don't know, maybe more consistent with write B here. This P1b are like E's, and this is like F's. So first column, zero column, and minus first column. And the formula says follows. So zero column, which is like Heisenberg, is more or less proportional to Heisenberg algebra, which we had here. I usually denote by this sign some numbers, which I don't want to write down explicitly. And these currents, it is convenient to not to write down just one generator, but introduce the whole currents, are vertex operators. So up to some normalization, they are just exponents of the Heisenberg algebra. This construction is called Basinization, and it is quite natural, quite often appears in the study of W algebras. This was one of the definitions of this toroidal algebra. Before people realized that all of them are the same, the algebra was defined in different papers, and this was a definition by paper with 5 authors. F is a Fagin, and one of these S's is a Sharaisha, and Y is Yanagida. So this is representation of one Fock model, and in order to be closer to W algebras,
Misha? Yeah, Misha.
yes.
May I ask you, as the line, vertical lines can
I write this line as a vertex operator?
Yes.
No. In general, no. There are some other generators which can be written as vertex operator, but they are not PAB. Maybe I should stop. Are there any other questions? Okay. This algebra is actually Hopf algebra. It has some sort of quantum group. It has a topological coproduct. And using this coproduct, we can take tensor product of the Fock models. I can tensor product of n copies of Fock models. And it was proven by different people. Maybe first who observed it was Miki. Then paper by Fagin, Sharish, Yanagida, and to go more authors, and some language by Andrei Negut, that action of this toroidal algebra on this tensor product factors through the QW algebra for GLM. And again, in some sense, one can think of this algebra as a limit of this W algebra for GLM, where n goes to. Okay, this is what I wanted to say about W algebra. So I will not use this W algebra actually, but I will use formulas like this. So what we will do in the representation theory, we take something from DAHA story, and also take something from this Basinization techniques, and somehow combine them to obtain our results. So this is why I talk about, another reason why I talked about this. We will have formulas like this. And after all this preparations, I should say something about what we're going to do, and this have something with previous talks on this conference, something common. So, as I said, in geometry, we can take the Hilbert scheme of k points in C2. This is well-known smooth manifold. There is an action of the two-dimensional torus on this space. This torus actually comes from the action of the C2, and then this action gives us action in the Hilbert scheme. Fixed points on this torus action are labeled by the partitions, and I denote them by P lambda. So lambda is partition, and number of boxes, lambda is actually equal to k, in order to have this point on Hilbert. Then there is a natural construction, generalization of the regional Nakajima construction of the action of this quantum toroidal algebra on the direct sum of the equivariant k series on this Hilbert schemes. Equivariant with respect to the torus action and maybe also localized. Okay, I don't have time place to write. It was constructed. It was constructed in 2 papers by independently.
Please mute yourself unless you are.
Okay, it was. I can proceed. Yes. So there is an action of this toroidal algebra on direct sum of this equivariant k series, and representation obtained in such way is actual representation which we had previously. So it is the same representation which we obtained in the transaction of symmetric functions, or Fock model which we obtained by Basinization. This third construction of the same representation, and fixed points correspond to Macdonald polynomials. So of course, there is some issue about normalization, but here I just ignore this. And this, okay, but from this geometrical description, we have another basis in the same vector space. Namely, there is a so-called stable envelope basis. In this case, we have k-series stable envelope basis, and they are defined in papers by Openkov. In cohomological cases, in his papers, Molik, in elliptic cases, in his paper Zaganagic, and the Merovli k-series case is written just in his paper. Now, this basis also will be labeled by partitions, of course, lambda, but now it depends on the additional parameter. In principle, it can depend on many parameters, but here we have only one because the Picard group of this manifold is one-dimensional. One can think, for example, this parameter is this parameter belongs to the real line, except some finite set of walls, which are now in this case belong to all rational numbers, and this basis is piecewise constant with respect to this parameter. Of course, if we just piecewise constant on this space, this set is a bit unclear, but for any given lambda, the points of discontinuity are rational numbers with denominator less than k, number of boxes in lambda. So for any given lambda, the points of discontinuity are isolated. So this indeed makes some sense, piecewise constant function. For example, for any rational, numbers n prime of n, we can define basis as n prime of n plus epsilon if you want, and s n prime of n minus epsilon. So neighborhood from the up and neighborhood from the below. This basis interpolates other known bases in the space of symmetric functions. So, for example, if with parameter omega is 0, these are just sure functions. And this, if this parameter goes to infinity, these are Macdonald polynomials. And it is defined, it has some geometrical definition, but algebraically, at the end of the day, they are defined in terms of three properties, which I call triangularity, integrality, and window condition. Triangularity means that if we expand this base in the Macdonald basis, I use M instead of P, which are related by some normalization, then only mu less than lambda appears here. So this basis has a triangle decomposition. The transformation matrix from this basis to Macdonald base is triangle. Another property is integrality, which states that these elements belongs to the can be expanded in the sure basis with integer coefficients. Coefficients which belong to this ring of Laurent polynomials. And from this, it follows that from this and this term M, it is quite easy to see that these functions C are also polynomials. And there is a third property that this polynomials has somehow bounded degree, bounded from below and bounded from above. I will not use, unfortunately, I will not use this window condition in the talk, so I wrote it a bit with dots, a bit unclear. Okay, so this is a definition of the basis.
May I ask a question? Is it polynomial by what variables?
It belongs to a ring of symmetric functions. So if you want to use the polynomials of P1, P2 of Newton power sums, P1, P2, and so on. Or symmetric polynomials on some variables y's, and we have infinitely many such y's. Okay. Okay, and so this is a definition, and there was a question how to describe them, and for example, how to describe matrix which goes from which correspond to the wall, which goes from this S lambda n prime of n plus epsilon to S lambda n prime of n minus epsilon. And several years ago, Andrei Neguts and Zhenya Gorsky conjectured that actually this matrix has to do with something about quantum affine GLN, where n is a denominator of this rational number. Namely, they conjecture that there is an action of the affine quantum group UV of GLN on the space lambda, such that the plus basis correspond to so-called standard basis, and minus basis correspond to co-standard basis. And so we had space on which we had action of the quantum toroidal GL1, and conjecture there is another algebra principle unrelated, which acts on this space. I would say that in one that probably this should be considered as some sort of duality, like GLN-GLM duality in integrable systems in the computation theory. Here we have the simplest case, GL1, GLN duality. Actually, two algebras on the same space. They do not compute, but they have some joint integral systems, like in theory of KZ dynamical equations. Okay, that was a conjecture. It was supported by quite non-trivial calculation by Andrei Negut, who showed that that action of the Heisenberg algebra, this UV of GLN, on the standard basis, given by the same formulas as an action of the certain Heisenberg subalgebra and toroidal algebra. This is Heisenberg algebra, which corresponds to certain slope and prime of n. So to each line in the toroidal algebra, each line which goes through the origin, we have Heisenberg subalgebra, and Heisenberg subalgebra which slope and prime of n correspond to Heisenberg subalgebra of UV GLN. So in particular, as I said, we have action of two algebras, quantum affine, and okay, maybe I should write it here, and toroidal, which both act on space. They share the same Heisenberg in some sense. So here we have the most natural Heisenberg, which commutes with SLN, and here we have not quite natural, but twisted this Heisenberg with some slope. They coincide. And other elements, of course, are different. There's no such subalgebra here. There's some sort of duality. And this fact was conjectured by Zhenya and Andrei, and it was proven last year in the paper by Andrei Smirnov and Yasha Konov, and their proof is geometric, based on the ideas which come from 3D mirror symmetry. Let me say just a few words about the idea. They consider a pair of dual manifolds with respect to this 3D symmetry. In this, they are usually denoted by X and X shriek. And in this case, they are both Hilbert hymns of key points on C2. Then for each of them, one can take some elliptic stable envelopes, and take the limit to k-theoretic envelopes. And for one of them, we take k-theoretic stable envelope with a special value of the parameter of the slope and rational and prime of n. And they showed that this actually on the dual side, they correspond to the fact that instead of X shriek, we consider its invariant subset with respect to certain finite subgroup. So this omega belongs to Picard lattice of X tensor R. So in dual language, it corresponds to the group of flavor symmetries of this manifold. So we can take certain subgroup generated by this element. This element has finite order because the corresponding elements, and take invariant part. And this invariant part, it will be Nakajima pure variety, and then it was the result of anti-negative that correspond to standard base. Our approach will be pure algebraic, so we will not use anything of this, but I like this point of view, so I try to say something. Maybe I also like the idea that we have here 3D mirror symmetry, and on the algebraic level, it corresponds to something like level rank duality. This fact appears also in some other examples. This corresponds. Okay, and now what we are going to do, we are going somehow to reverse the logic. So in the Gorski-Negro conjecture, we had space lambda. We knew that there is an action of the quantum toroidal algebra in it. And the conjecture that there is an action of the quantum affine algebra of GLN. As I said, we reverse the logic. So we start with the representation of quantum affine GLN, and then construct on this space action of the quantum toroidal algebra. Some of the properties, at least, that we should obtain the same model, like lambda or Fock model, and the standard Heisenberg. And we obtain the model which is twisted, such as the standard Heisenberg, would correspond to this red thing, red line. So Heisenberg with slope and prime over n, or Heisenberg which belongs to this UV of GLN. So if we wanted to do this, in this sense, we obtain twisted Fock model. If we wanted to do this, and we already know where to map Heisenberg subalgebra of this quantum toroidal algebra, and it remains to say where to map other Chevalier generators. And first idea, of course, would be to write down the in terms of this quantum affine, but this might be not possible because this is a duality. But there is some more interesting ingredient, namely vertex operators, and we will finally write down these Chevalier generators in terms of the vertex operators. Okay, so this is our goal, which maybe now explain in a bit more detail. So we take start from the Gorski-Nyev conjecture that on the one space we should have action of two algebras, quantum toroidal GL1 and quantum affine conjecture toroidal GLN. And we start with the quantum affine GLN and using additional stuff like vertex operators, like fermions, if you want, for some for special case. We construct action of the quantum toroidal GL1. In principle, then we will have precise formulas, but our approach, as I said, we use both precise formulas with vertex operators and also double affine Hickey algebra. Now, if there are no questions, I'm going to explain a bit how we actually do this. Okay, so we want to construct some additional action on this Fock model, and it is well known this Fock model has semi-infinite construction. So it has a basis of semi-infinite wages, and actually this is the standard basis which we had in Gorski-Nyev conjecture. So if you want to prove the Gorski-Nyev conjecture, which says not just we have an action, but this action, in this action standard basis should correspond to the stable envelope basis, then it is quite natural to look the semi-infinite construction. So this is the base of semi-infinite wages. If you want to prove something for semi-infinite wages, it is quite natural to start from the finite wages. And even before going to the wage power, it is quite natural to study just tensor product. This is where we start. So we can see the tensor product of the n capital standard evaluation representation of the affine GLN. So ordinary GLN has n-dimensional representation. Affine GLN has this representation Cn with the space of Laurent polynomials on Y. Y is here the formal parameter. So this algebra X actually on the any of them, and using coproduct X on the tensor product. One can ask who else acts here, so who commutes with this algebra. And due to Chauvel duality, affine Hickey algebra also acts here. And it is quite easy to write down this algebra. So yi, it is just y which acts on the i's factor in this product. And t's are R matrices. It is well known that these R matrices satisfy quadratic relations of Hickey algebra, and of course braid relations. This is, as I said, toroidal algebra is related to Hickey algebra, so this looks quite close to what we want. But as I said, toroidal algebra is related to double affine Hickey algebra. So one can ask, is there any double affine Hickey algebra? And this is actually our first theorem. That this action naturally extends to the action of the double affine Hickey algebra. here write down some formulas. It may be just difficult to follow them. What maybe is important is the following: that we can, if we define natural gradient on this space, then all y's will have gradient n, and all x's will have gradient some other number n prime. And at the end of the day, it will be the same n prime as we had in the Gorski-Nyegut conjecture. So this extension of the algebra to the action of the DAHA depends on the additional parameter, which is integer parameter, which is n prime. So in principle, we have many actions of DAHA, and we can take many limits of them, but here we have to specify n prime, and n is a rank of the dual algebra, fine GLN, and n prime is hidden in the construction of this DAHA. Okay. And Gorski-Nyegut conjecture says again that the standard basis corresponds to the stable envelope basis, and on the practical level, it means that if we take standard basis, then it should satisfy the properties 1, 2, and 3. Here, as I said, standard basis is a semi-infinite wedges. If it should satisfy properties 1 and 3, it's natural to believe that finite wedges satisfy some similar properties, and even before wedges, just decomposable tensors satisfy some properties. And this is subject of another theorem. It is true. They satisfy, but unfortunately, we proved only for first two properties, triangularity and integrality. We checked in some examples that window conditions looks to be holds, but we don't have proof. It's interesting that now before we had window condition in terms of the symmetric Macdonald polynomials, and now we have non-symmetric. I wrote non commutative, but write not symmetric Macdonald polynomials. Okay, this is what we had for just tensor product. Now we come to the wedge power. So take now, instead of symmetrizer, anti-symmetrizer, given by more or less the same formula. We get wedges. We apply this anti-symmetrizer to decomposable vectors, and this is also an opposite theorem. But here, on this point, new ingredient come to the story, maybe more or less the last ingredient, namely vertex operators. These vertex operators were first probably defined by Frankel-Stich as a natural Q analogs of the vertex operator in conformal field theory. For example, they should satisfy the vertex matrix element of the vertex operators in CFT satisfy Knizhnik-Zamolodchikov equations, and matrix elements of these vertex operators satisfies QKZ, Q Knizhnik-Zamolodchikov equations. Of course, here we have quite special situation. In this case was studied in these papers. We have 4 types of vertex operators. So it maps from the nth wedge to n plus first 1 or to n minus 1, and also tensor with this vector representation, vector evaluation representation. And we have 2 choices. We can multiply on the right or on the left. And the operators of the first operators are called psi, and these operators are called phi. In Miva notation, this is like operators of the first kind and second kind. So they are defined by the properties they are intertwiners, and it also requires some normalization. And in simplest case, for phi, it's the following. So phi is a decomposed sum on Z, and phi j acts by just adding one more vector ej to the lambda. By this form. So in not Q-deformed case, it would be just operator which take wedge product with some basic element or take derivative with respect to some basic element. And now lemma. First of all, there is a surjective homomorphism from the quantum toroidal to S minus of Hn, symmetric spherical Hicke algebra constructed by the important S minus. This is more or less a reformulation of the theorem which by Shukhin-Vasserov, which I mentioned before, that we have corresponding homomorphism to S plus. But what's new that we can write down image of this homomorphism which acts on some space Cn, some nth wedge power, using the vertex operators. Here is how the formula looks like. The bilinear combination of these vertex operators. And here I also draw the picture, maybe to somehow explain what do I mean by twisted model. So in ordinary representation, so Fock model, this is a gradient, and in Heisenberg part we have H's with any numbers with positive and negative. And for E and F the same. But if you take twisted, then this red line which goes through the origin will have some slope. For example, as in this picture, it can act only with even mode, shift the gradient by even number. And two other lines which correspond to E and F, simple roots, they are become odd. In sense, they are expanded in Z. You have only odd modes. So if you take ordinary representations, then E, F, and H act by any mode. But if we take twisted representation, it could happen that not any mode is okay. We should somehow assume certain mode. And this is, in this case, we usually have something like that. Okay, after this preparation, let me state a bit vague, give a bit vague statement of the last theorem. This theorem says that if we take nth wedge power as a standard representation and take the limit where n goes to infinity, then on the one hand we obtain representation of the quantum affine GLN, and this well-known result. And on the other hand, we obtained a Fock model of the quantum affine GLN, quantum toroidal GLN. In order to compare, so in this space, we knew that there are two actions. First of all, there is an action of the quantum affine GLN and also spherical Hicke algebra, but there is this surjective homomorphism from the toroidal to spherical Hicke algebra. So we have action of two of these algebras indeed on the finite wedge. But it appears that in the limit something non-trivial happens, like appearance of the new central charge. So practically we prove this theorem somehow considering different cases. So we define certain subalgebras, the quantum toroidal algebra, if you want, plus or right subalgebra, left or minus subalgebra, and this bottom subalgebra. And we show that of course, there is an action of quantum toroidal on the space, but generators from the right subalgebra, they converge under the sum assumption Q and V, as here. Generators on the left converge on the another assumption Q and V. And these generators converge always, and we show that actually all these functions which are obtained after the limit, we obtain just rational functions. So this convergence is the sum of the infinite geometric series. All these functions agrees and can be glued to one representation of the whole quantum toroidal. So we collect many facts in the finite case of about this vertex operators, for example, and then prove this conduction. Okay, there's no question. Maybe people generally tired. So this is my last slide. There are several questions which remains untouched. First of all, as I said, this is some sort of duality like G1 GLN, but on the level of GLN, I used only quantum affine algebra. It is quite natural to expect something similar for toroidal algebra, and this is work in progress. At least, I mean, there is some progress on this question. I would say the following. Another question that I constructed duality between representations. So on the one space, I have constructed action of two, in principle, different algebras. But if quite often in series integrable systems, this is related to duality, to the fact that the corresponding, say, Gaussian or commutative subalgebras, there are certain commutative subalgebras in this algebras which coincide or at least has spectrum has a semi-simple set spectrum of the same basic elements. And there are some reason to believe that this is possible also in this case, but it is not done. Okay, question number 2 is about a window condition for non-symmetric polynomials. As I said, for them, we need 3 properties in order to state a certain basis and stable envelope basis, and we proved 2 of them in the theorem, and the third was somehow checked, but in generality, it remains a conjecture. And the third question is there any geometrical meaning of our construction? I don't know, in terms of maybe after 3D mirror symmetry, this geometric meaning should be on the clear variety. Anyway, it would be interesting to find some meaning, otherwise just non-clear computation. Okay, maybe there are more questions, but I stop on this 3. Thank you for that.
Is there any question? Questions from no questions. Let's thank speaker again. So let's thanks again for the talk.
Thank you for listening.